Good morning. Today's a fantastic day. I'm going to be competing in round 651. Starts really soon. I'll be commentating a little bit more. If you're interested in the solutions, those will be at the end, so you can just skip to the end. If you want to see those, if you want to see me struggle, it's a good thing to watch. Let's consider all integers in the range 1 to n. Among all pairs of distinct integers, find the maximum possible GCD of integers in a pair. Wait, what? Oh, n 1 to n, so it's just n over 2? Yeah, I think it's n over 2. And 2 looks right. Do I have a proof for that? Not totally. Seems to be fine though. There you go. It's an array of 2 n integers. It wants to compress A into an array B of size n minus 1. So you want to, you want to remove n plus 1 things. He first discards exactly 2 elements from A. Then he does the following. Remove 2 elements and append their sum to B. Okay, another GCD, man. Compressed B has to have this following property. The GCD of all its elements should be greater than 1. So we could make them all even or all odd, maybe? We could probably do other things as well. Help him find a way to do so. Can it be impossible?
I'm not sure how long to set it for.
We have company. We have company.
Understood, sir.
I'm kind of confused. The 1 base indices of the 2 array can be proven that it's always possible. I should read this part of the problem. Alright, so you discard 2 elements, and then after that you want to pair up all the evens and all the odds. So if you have an even number, if you have an even number of evens, then discard either 2 evens or 2 odds. Otherwise, discard 1 of each. And then print out all pairs of evens and pairs of odds. Okay. So int n equals okay, so then int evens so if it's even, and we print indices at the end. Yeah, okay. So if, well, you can just make these array lists. So we've got these 2 lists, and now Cool. So now we have a list of evens and a list of odds. So now we print, what do we print? N minus 1 lines. So we want to go from the back, I guess. Well, when it gets removed, do the indices change? Three, 6. Oh, then 4, 5. So it doesn't look like they change. Okay, so that's even easier. Going to I equals 0, I plus 1 is less than evens dot size, plus equals 2. This out evens dot get I plus evens dot get I plus 1. But both of these are 0 based. Well, let's just add 1 here. And then we need to do the same thing with odds. But minus odds dot size. Ooh, yeah. Okay, so now if evens dot size mod 2 equals 0, and if evens dot size is greater than 0, evens dot remove. Well, from the first one, else odds dot remove 0. Okay, so now that should fix it. So let's try some example. Oh, Nick's out of bounds. Okay, 2, 4. 2 plus 4 is even. Cool. 1, 3 is also even. And 1, 2. We should only print 2 of them, right? Oh, this is second test case. So 1, 2. Yeah, that would be fine. And then I assume that's right. Do we need print writer? No, looks like small output. All right, so that took way too long. Yeah, man, look at that. Jeez.
Problem without wrong answer test 1, sir.
Wrong answer test 1? Seriously? Well, I guess I should read it then. N is at least 2. Yeah, okay, that's fine. Oh, this should be I plus 1. 1, 2, 3. Okay, yeah. So I was getting this last test case that I didn't read wrong. Now I should put one more number. Cool. All right. Awesome. Let's move on to C. They start with a number n and play in turns. In a turn, each player can make any one of the following moves. Divide n by any of its odd divisors greater than 1, or subtract 1 from n if n is greater than 1. Divide n by any odd divisor, or subtract 1. Parity seems like the move. Or I guess not. So if it's 2, then you win. So you want to get to 2, right? 2 is the only way to win. So 1, 2, okay. And then 2 can't come from 4. Oh wait, yeah, it can. 2 can come from a lot of things. I guess this is a good example. So 3, you lose. 3 is a losing. Wait, 3 is a winning state. Yeah. So 3 wins. Any odd prime wins. Any odd number wins, right? Like, they don't give us any odd numbers, but any odd number wins. And if it's an even number, you lose. Except for 2. So 4 loses, 6 loses, 12 wins. Why does 12 win? How does 12 win? 12, you turn into 11. 11 you can divide by 11. Oh, yeah, you can divide it by things. I see. So any odd number wins. 2 wins. Well, if you have any odd divisors, you win, right? If you have an odd divisor, you take out all the odd divisors your first turn. Then the person has just like a power of 2. I guess, what about 6? 6 is an interesting case. So if it's, okay, so if it's 2 times like some odds, then that's interesting. I'll figure that out later. If it's 4 times some odds, then you win. If it's just 4, then you lose. If it's just 2, then you win. What about 2 times 3 times 5, for instance? So if it's 2 times 3, if you take out the 3, you lose. If you take out the 5, well, that's the same as taking out the 3. If you subtract 1, from 30, you get an odd number. So if it's 2 times a prime, then that's going to be a losing state. Otherwise, 2 times anything else is a winning state. Except for powers of 2. So 2 to the anything will be a losing state if x is greater than 1. Is that everything? Okay, so let's see. It's a power of 2. You have no odd divisors. You have to subtract 1. Now you're odd and you lose. Okay. If you're 2, you win. Okay. If you are 2 times a prime, the other person can either bring you down to 2, because then you win, so that's bad, or they can subtract 1, and then it's odd and they lose. Okay, so that's right. And if it's 2 times more than 1 odd prime, then you take them to 2 and a prime. Okay, so that's right. So that's all the cases. Cool. All right, so yeah. So we have our n, and okay, so if n equals 1, okay, so if, who goes first? Come on, tell me who's first. This person moves first, so if it's this person, then they win. Otherwise, this person. Okay. So if n equals 1, sys out, lose. Else if n equals 2, sys out, win. Else. Okay, so if it's a power of 2, then you lose. If integer.bit count of n equals 1, then sys out, lose. Okay, so otherwise, it's not a power of 2, then 2 times a prime will win. Oh, I guess if it's odd. Else if n on 2 equals 1, sys out, then you win. Okay. So if it's, what if it's n? If it's n, or prime, okay, so 4, well, yeah, 4 and I equals 2, I times I plus n plus if n mod I equals 0, and true. Alright, so now if it's a power of 2, we lose. But we know it's odd. Cool. So now if prime n over 2, then we lose. Wait, if it's a prime times 2, yeah, we lose. Otherwise, we can get there, so we win. So many cases, man. Give me C. Nope, I said C. C, please. What is going on? What? FAA, FAA, ooh, not right. Interesting, okay. So I get the last two wrong. 6 and 12 I get wrong. So 6 is 2 times an odd. This can either reach 2 or an odd. If it reaches an odd, it loses, because an odd is a winning state. If it reaches 2. So if this is prime, n divided by 2 is prime. Oh, yeah. FAA, FA, FA. Looking good. So that was a really cool problem, actually. I thought. So it took way too long, but again, very good problem.
Road answer is C on problem C.
Ekner Wall is doing this round. Awesome. Good to see him. Ray has, or this person has an array of size n. A subsequence of A is defined as a sequence that can be obtained from A by deleting some elements. Yes, we know what a subsequence is. We are not fools. Consider a subsequence S of A. He defines the cost of S to be the minimum between the maximum at all odd indices and the maximum at all even indices. So you like split it up, and it's whichever maximum is smaller. Okay. Note that the index of an element is its index in S rather than its index in A. Of course, yes. Well, it doesn't matter if it's 0 or 1 indexed, but fine. Help him find the minimum cost of a subsequence of size k. Interesting. I see. So either only your even positions matter, or only your odd positions matter in your subsequence. And the other half you can just ignore entirely. So I suppose maybe we can binary search what the answer is. Yeah, binary search then greedy. We're gonna need 2 greedies though, I guess. One for if we assume it's evens, one for if we assume it's odds. Yeah, so if we, so what is this gonna look like? Binary search the answer, and then we have like a set of legal things. And if it's, yeah, then we just do it twice. Okay. Okay, we can do that. Is it single test case? Convenient. And come on. So then so the int legal bound and int k. So int min, how big can these things be? I guess we'll just binary search the full range. So int min equals 1. Surely 1's always possible. Or you can't do better than 1. Yeah, okay. Max equals 1. This array, the legal bound of mid, and k is equal to k. Okay, so if it's possible to do a min less than or equal to the legal bound. So if this is possible, then max equals mid. If it's not possible, min equals mid plus 1. Because we need a bigger minimum. All right, cool. So now we just have to solve this method, which should be really easy. Oh, and then at the end we print the answer. So this method is just a greedy, or two greedies. But we'll do this greedy first. Okay, so int count equals 0, return count greater than or equal to k. For int I equals 0, I is less than, or okay, so, well, yeah, I don't think that matters. Doesn't matter. So if count on 2 equals 0, okay, then, well, I guess then we can just always take it, right? So then count plus plus. Else if a at I is less than or equal to k, then count plus plus. Then we also need go to, I suppose, which will invert these. No. 3. Why would that be the case? Okay, so oh, this isn't even close to right. This should be but that should make it worse, right? Like that should be even more extreme. Okay, so in mid 2, count equals, or in go, count equals 3. Less than or equal to legal bound. And this is why I suck at easy problems, people. Because I can't do this. Right, so that's fine. That's fine. Let's get rid of these. All right, moving on. Oh, wait. Yeah, it shouldn't need print writer, so that should be fine. Unless we hear otherwise. You have two binary strings, s and t, of length n. He wants to convert s to t using the following operations as few times as possible. In one operation, you can choose any subsequence and rotate it clockwise once. Any subsequence. See, now I need the definition of a subsequence. Oh, he can choose this, this, and this. I see, that's an interesting thing. Okay, do we need to turn S to T or something in the minimum operations? Yeah. Well, we can always swap, so it's always possible if there are anagrams. You're never going to want to pick 2 ones in a row in S. Like, that doesn't help, because if you pick 2 ones in a row, then you could have just not picked the second one. So rotate it clockwise, right? Rotate it clockwise once. Also, each position is only going to be picked once. This seems like a very easy problem. Does it have a ton of solves? It's got a few solves, not as many as I would expect. I wouldn't expect this to take this long. I guess it took him 4 minutes, so that's more on par with what I would expect. And this person did it first. Okay. Alright, so let's see. How do you do this? So, I guess it being circular might be annoying. That might be why it's hard. So if you have like some ones, well, all right, let me just like come up with 2 strings. So we have several zeros and some ones. Okay, so now if something matches, we can just effectively ignore it entirely. So now we have 1 1 0 0 0 0 1 1. And what we need to do is we need to pair these up, I guess. Yeah. Oh, so it's like a bracket subsequence problem, or a bracket problem, I think. Another question is find the deepest, like how deep it is the number of turns. We don't have to extract it, nice. So yeah, so we've got this bracket sequence, or I guess we have a bunch of +1s and -1s. And we need to, like, when we pair them up, we want the deepest nest to be as shallow as possible. Does the start matter? I'm like kind of confused because you can think of this problem as a circular problem, but I'm like trying to brute force the start or something, which is weird. So maybe I'll just like write some +1s and -1s here and then see what would happen. So we take these, this moves like that. Oh, we can't move a -1 to a -1. So we just have to pick a sequence of plus, minus, plus, minus. and then minus plus, and then plus minus. So the answer would be 3. Yeah, so I think you can just do that. Yeah, sure. Sure, why not? So that's n log n, tree sets. Am I gonna get dinged for that? I might. It's a very real possibility. I don't like getting dinged for tree sets. It's not fun. Suppose I could optimize it to use a Fenwick tree instead if I needed to. So what operation do I need? I need find the next. Oh, does it matter? What if I start with a minus though? Does that matter? Or is that never optimal? It's plus. Yeah, surely you always start with the first one. Yeah, duh, that's stupid. Okay. Of course. So I can either have like a next highest. I guess I'll just try it with true sets, because it should be n log n, which should be, I'll try it. I'll try it. Wait, what is this? This is, did I get D? Did I solve D? Oh yeah, binary search. Okay, let's try it. So we have both of these lines, and then well, so if this, okay, so if line 1 at I equals line 2 at I, then we'll just leave this the same forever. So then we just can continue. Otherwise, if line 1 at I, then pluses dot add I, else minuses dot add I. Okay. Oh, sorry, if this is equal to, let's make it a 0. Alright, so now, if pluses dot size not equal to minuses dot size, then sys out -1 and return. Oh, sorry. Okay, so otherwise, we need to start from the minimum and go from there, right? So if while not pluses dot is empty, and turns equals 0, so it's okay. So there's definitely a better way of doing this that doesn't use tree sets, but I think this should be fine. So if pluses dot first is less than minuses dot first, and we do it with this, otherwise we do it with this. Okay, so All right, so now we have these two tree sets. So int at, well, okay, so int position equals -1. Well, true. Int higher equals a dot higher position. If higher is greater than null, then continue. Your b higher equals b dot higher higher. If b higher equals null, then continue again. Otherwise, a dot remove higher and b dot remove higher. And then we can, well, I guess we can just keep going. Oh, then position equals b higher. Then we keep going from there. Okay, and then turns plus plus. What? Why is this unreasonable? Oh, this should be break. All right. So we got the first one, get the second one, keep removing, do an entire pass through until we can't anymore. Then we increment our turns. We print the total number of turns. No such element exception. It's not empty, what? Oh, be higher. So now the real question here is less of whether it's right and more of, do I get dinged for using Java? Or do I need to optimize it to like something else? I think I can optimize it to using a Fenwick tree if I need to, which should definitely be fast enough. It's 2 seconds, I don't know, should take about like 1.5. It's my estimate. But you never know. Oh, less than a second. Alright. So we have an hour and a half left, and it looks like most good people are going for E2. Alright. So yeah, let's try let's read these, I guess. Interaction. Woohoo! Alright, note the only difference, blah blah blah. Oh, wait, is the number of query constraint on the queries. I see. So it sounds like just submit twice, right? The limit of 14 queries applies to each test case, not to the entire input. What is it here? Limit of 11 queries, okay. You're given a tree of n nodes numbered 1 to n. These two people select choose two secret distinct nodes in the tree. You need to find out both of the nodes. You can make the following query. Provide a list of nodes, and you'll receive a node from that list whose sum of distances in both the hidden nodes is minimal. To both the hidden nodes is minimal. So we give them some nodes, and they're like, yeah, the closest, if you go from like A to B through your node, the distance is minimal. If there are multiple, you receive a random one. You also get the sum of distances. Oh, we also are told that sum. I see. Yeah, I know what a tree is. Thank you. More formally, let's define two hidden nodes as S and F in one query. I don't want... Nope. Alright, you can ask 11 queries. with 1,000. So you need like log n plus 1, it looks like. And here you get log n plus a couple. Oh. There's an idea. This feels super Centra decomp heavy, in my opinion. So like if you pick any of the nodes on the path, you'll get that node. But then, I don't know how helpful that is really. Like it's tricky. I'm not sure. Yeah. Is it important that it's not adaptive? I feel like with this, it can't really be important. Because you have more than 10 to the 6th people competing, right? So there's just too big of it. If you like, if there's a single pair, because like the only thing, yeah, it being not adaptive can't be important. There's not enough security for a randomized solution to make that matter. Okay, so this is a cool problem, but it requires a bit of rather good strategy, I guess. Let's see, how good are the people who are getting it? They are legendary grandmasters. But I guess more people are getting it too. Just not getting the rest of them? Maybe some people are just like only looking for interesting problems to solve. They find these interesting, so they're doing them. Oh man, William, what are you doing? Okay. So Do I want to even have a node on the path or not? Well, I could, if I need a node on the path, I could get it by just giving them all the nodes, and they'll give me some node on the path. So maybe let's just worry about that now. So maybe I have some node on the path. I have some node on the path, and I also have the distance of the path. Oh, if the hard part is the difference between 11 and 12 queries, that would be pretty funny. Yeah, I think it might be. Because I think 11, I think I can do it in 11 queries, but I don't think I can do it. I think I can do it in 12, but I don't think I can do it in 11. That's pretty funny. That's interesting. Okay, so you get a node on the path, and then you binary search how far out to go. So once you have the farthest node, you know the distance. Yeah, okay. So that's one idea. So let's, I guess, just write it down so we don't forget it when we move on to the next one. The idea is query everything to get a node on the path, and then after that we can binary search the distance from that node to the farther of the two. And then once we have that, we just query all nodes from, or the right distance from the farther. So this will be one query. And then this one takes 10, unfortunately. And this one takes 1. So I do it in 12. Yeah, I do it in 12. So if I could cut one query off, that would be super convenient. I guess, Oh, wait. I feel like this is definitely the F1 solution. This is, it's kind of funny. Yeah, 11 queries, huh? That's, man, I'm so close. I'm one away. How do I just trim that one query? Can we maybe not query everything? Well, all right, so what do we do? 1 query to everything, 10 for the binary search for the farther from what we got from the first one. And then after that, we do 1 more to find the other endpoint. If we ever get a node that's too far, yeah, okay, I think that might be it. So if we ever realize that we're too far out, then we can walk in to find that first node. So now we should start binary searching the other half. Because like we can walk in from there. I find it interesting that there aren't more solves in F1, because to me at least there seems to be a huge difference in difficulty. F1 seems to be very doable and F2 seems to be a lot harder, for my solution at least, because I'm stuck at 12. I guess I don't want to burn too much time, right? Like the longer I wait to write up the solution, the more points I lose for F1. So it might be worth it to just get the points now and then worry about F2 later on. Yeah, okay, so I'll just try that. So how does this input format work? Multi-test case, that's annoying. Why would they have to do that? So first we're given n. We have all of our nodes. Then we read them all in. Okay, so after that, we're given a bunch of edges. And then do that split backwards. All right, so now we have our tree built. Okay. So now how do we ask this? Followed by C distinct integers in the range 1 to n. Okay, so first we get the root. So print out question mark and And then we need to print I plus the space okay, out dot flush. Alright, so that'll get the root. Oh, now we have to read the root, right? As a response, the node. And the minimum sum of distances, the hidden nodes. So node equals fs.next minus 1. Okay, and then int distance equals fs, or yeah, okay, sounds good. All right, so then we have this. Cool. So then we can just try this a bunch, right? Static. Well, okay. So yeah, static void try distance. So we're going to BFS from the root node, which is going to be some node on the path. And then we need to find the farthest node, and that'll be the high end of our binary search, I think. Yeah. That should be fine. Oh, yeah, okay. So one optimization we can do for F2 would be try like the centroid first. Yeah, I think I have some ideas for what we might be able to do for F2. Okay, add this thing to our BFS, and then we're done. Okay. So BFS from the node to the root. Alright, so then max will be equal to the farthest node of all of them. So while min is not equal to max, int mid equals min plus max over 2. And then, well then what? Okay. So try distance nodes from the root. What distance do we want to try? I guess try mid. Okay. So now, when is this bad? So if distance returned is greater than distance between answers, that means we've gone too far. So that means max equals min minus 1. Otherwise, that means we haven't gone too far. So min equals max, or mid. And then this needs to be plus 1. So it's not an infinite loop. Okay, so this should run a reasonable number of times. And yeah, I think centra decomp would be what you would use to get the extra query. Okay, but we'll worry about that after we ACN this. So, oh, I feel like it's definitely centra decomp. Ah, that feels so right. Okay, anyway, yeah. So then, we just do the final query. So node or int n1 equals node returned. Int n2 is going to be equal to, well, then we need to try distance, I guess, from nodes. Where is the root going to be? The root will be, well, just the root. No, it'll be n1, JK. And then the distance will be just between answers. Okay, so then int n2 will be equal to node returned. And then we can fix out 1 plus n2. Or, all right, how does this interaction work? To guess the answer, exclamation point, plus. All right, so then what's that next? Okay, so print it, blah, blah, blah. Read the next thing, do the next test case. Okay, so then this should all be fine. We just need this try distance method now. So this should be pretty simple to write, I think. So BFS from nodes it from, and BFS to, or I guess nodes, okay, duh. So then array list node nodes. So if our distance is equal to the target distance, then use .add mn. All right. Okay. So where were we? We were this try distance method. And now what we need to do is ask the query. So sysout question mark plus use.size. And dot index plus a space. Okay, so okay, this is just node returned equals fs dot, oh, we need our fast scanner. It is node then distance, right? Yeah, node then distance. Node, minimum sum of distances. Okay, so then distance returned. What about here? Root distance, okay. Awesome. So I think this should be fine. Let's do a test case ourselves. 1, 2, 3. So they're gonna ask me 3 nodes. Okay, so what should I tell them? Hidden nodes are 1 and 3. Okay, so maybe I'll tell them 1 and the sum of distances is 1. That's the format. Okay. So now they ask me about 2 nodes. They're asking about node 1 and node 2. Or why would that be? Okay, should be an x plus 1. So now they're asking about nodes 2 and node 3. And I'll say node 3 is distance 1. Or I guess node 3, which is a sum of distances of 1. So now they're going to tell me it's 1 and 3. That would be correct. Yeah, so I think this should be fine. Wrong answer. Retest 2.
Program 1. Wrong answer. Test 2, sir.
It's a bit unfortunate. So we have, let's try just 2 test cases again, in case that's it. So this, okay, so 3, so the distance is going to be 1, and we're going to pick node 1. Distance is 1 for 3. Let's see. Going to be 1, 1, 1, 3. Oh, wait. That's because I'm telling you the wrong things. Yeah, it should be fine. So why Yeah, this is why. It's because it's node returned, but I want the last legal node returned. All right, so in this case, n1 equals the ans node. This one's equal to the node returned. But what will the ans node be? All right, so if it's too big, then we skip it. Otherwise, we want to do ans node equals node returned. Well, yeah, I don't know. Is this an issue? This is an issue. This won't work with my binary search. Well, I guess now I'm just doing 13 just for fun. My binary search is bad, but that's fine. So now I can do try distance nodes from the root, and the distance is min. Yeah, so this should fix it. This call here. I'm gonna resubmit this because I'm feeling lucky today. Should have added statements so I know why it gets wrong, like what I'm doing wrong. But maybe that's not necessary. Alright, 11th place. Not bad. So then, alright, let's go. Good job. He's doing his work. Okay, so now we gotta cut off a few queries. That's the goal here. In order to do slightly better than we are now. This is a good, I am a fan of problems like this. If you're gonna have two versions where it's like, this version is just do a better job of the previous version, it's not just like when you make the easy version just like a stupid problem that's just like, you know, like, I guess kind of like Usako does. I'm not a fan of that, where the easy version's like n equals 5, and it's like, okay, well, I'll just write the brute force, I guess, because then I get points for it. I think that's kind of lame. But here, I don't know, F1 was an interesting problem. Even if there wasn't an F2, F1 would still be a good problem. So I think that's why this is okay, or an example when this is okay. So I guess let's see. So we get the minimum distance. So there are two approaches that I'm considering using for this problem. One is like just going down the centroid decomp path, because that might work. The other, which is kind of unrelated, is instead of going down the centroid decomp path, I might be able to squeeze a couple of queries in my binary search. So like, how many does this take actually? Initially the gap is 1,000. So it'd be like 1,000, and then blah, blah, blah. So at the end it would be 1. At the end it would be size 1. Before that it could be size, well, if they're 1 apart, then mid will be equal to max. Yeah, so then it'd be size 2, size 4, 8, 16. Okay, so 2 to the 0. Well, when it's 1 apart, we do 1 query. This is 1. 2 to the 1 is 2 queries. So 2 to the 10 will be 11 queries with this here. And then this makes 12 queries. Or no, this makes 13 queries actually. Why 13 queries? Well, yeah, because we did the first query. We did the first query here. So I'm doing 13, and I need to be at 11. I think we can squeeze 1 out of this. Because in this case, there are 2 cases. So here, like here we actually have the answer. And here, we don't have the answer, but we're too big. But we can just take 1 step closer. So yeah, so we can like case out this to get rid of this query. So that will get us down to 12, which is what I initially wanted to do. We're still 1 short though. So maybe instead of doing that, we look at the centroid decomp idea. I've never actually like solved a problem using centroid decomp. So might be a little hand wavy, I guess. You need a pretty big tree in order for your samples to like make any use. Okay, so we pick some node and we query this node. What does this tell us? Well, it tells us the sum of distances. Okay, fine. And then if we query all future centroids, then if the biggest one of those okay, there are only, how many other centroids are there? There will be 2 in this example. So maybe we query these 2. So when we query these two nodes, then if we get something small enough, we can get rid of all but one centroid and everything on that path. So this is if it gets smaller. If it gets smaller, we can cut off like the original, like everything. If it gets smaller, we have a new root. And the max is equal to the distance to the centroid. Plus 1 maybe? Okay. If it gets bigger, that means that we keep the right center, keep the center we have, and decrease the max distance. So we should probably make an F2 for this. Yeah, all right, so let's, I guess, write this out more formally. So we're going to pick some starting node. Well, I guess the starting node will be the centroid. And then after we've picked the centroid, then we consider all, or I guess we just consider stuff that's the right distance from it. Yeah, so then consider stuff that's the right distance from it. And if the neighbor's distance is less than ours, then change the root. Wait, this has nothing to do with centroids at all. Yeah, the good part about the centroid, though, is that we cut off another free query. Okay, so that's beneficial, because if we have a centroid, the maximum distance is like 512. Or is 500, I guess. Yeah, so change root. So that's why we want to start with centroid. It might not matter at the end, but it might be helpful. So if our neighbors are less than ours, change the root to him. So yeah, let's just kind of write this from scratch, and then we'll worry about it as we go. Maybe that's a terrible idea. In general, that's just a bad thing to do. Okay, so we don't need this. We will worry about this in a minute. We'll also worry about this stuff in a minute. So let's just comment this out for the moment. So the first thing we're going to do is we're going to make the root be the centroid. So, or I don't know, maybe just the center of the diameter. I don't really know what a centroid is, so I should stop calling it that. But let's do this. So let's so this is going to need int dist1, dist2. So nodes, or BFS, from nodes at 0. Okay, so now we need the farthest. So let's return the node, return and BFS from end1 nodes for node and then nodes and then dot dist1 equals nn dot dist. All right, so then node n2 equals farthest. Then BFS from n2 nodes and then that for node and nodes. And then that dist, or dist2 equals nn dot dist. Okay, so now we have all of these things. So now we can find a center pretty quickly. So node best equals nodes at 0 for node nn nodes. If math dot max of nn dot dist1 nn dot dist2 is less than best or math.max best.dist1 and best.dist2. In this case, we can make best equal to nn. Okay, so now we have a starting point. And int min equals 1. Or yeah, min distance is 1. So this is like the distance from the root. Okay, so this isn't really the best, this is the root. The max is going to be equal to math.max root.dist1 root.dist2. Okay, so now we have these two bounds. So we're going to do this binary search. So the binary search will take, well, we've removed this query. We've almost removed this query, so it seems like we can actually keep this one. Is that right? The binary search takes 9 steps. We need the 10th for this thing. And then we need the 11th here. Ooh, that would be nice. That would be nice. Okay, so we're trying this distance from the node, from our root. So I guess this should be a node, maybe. From our root to the mid. Okay. So if the distance returned, int current best. We have an issue. What is the issue? The issue is that, how do we know? Yeah, we're gonna need to get rid of this query somehow. We need to know the distance from, maybe this is an issue. Yeah, this is why you think about things before you code them. Lesson learned. The issue is that we're gonna throw away our best node right away. Like, we're gonna find some other node, but there's not really a reason to do that. Should we also include ourself in the first query? Nice job, Anderson. Well done. Did you get this wrong or just slow? Both. Well, maybe I try and optimize my binary search for a bit. If I spend the first query, well, why am I worrying about this? So I spend the first query figuring out the distance from this midpoint. Yeah, so I have this first query. And now if it's in some subtree, Yeah, okay. So try distance from nodes from the root distance 0. So then the current best will be the dist returned. Okay. So now if it's dist returned is greater than current best, else if dist returned equals current best. Okay, otherwise we have this third step. So otherwise we switch the root and have the current best. So if we found a better root, that means root should be equal to node returned and we need to decrease max a bit, I'd say. So well, now current best equals dist returned. But I suppose now max equals mid. Because you can't take that step twice. I don't think you can do mid minus 1. I don't think that's a legal assumption. Oh, maybe it is though. So if it's 4 away, I guess let's look at 5. If it's 5 away, well, if it's 5 nodes, that's 4 away. But if it's 5 away, then you take, oh, this is tough. Yeah, this should only happen when mid equals 1, I think. All right, so then we have this, we have this, we have this. We need to keep that. This will be current best. So we need to keep this. So now, how many queries do we have? So this is 1. This will be 9, I think. So now we're at 12, so we need to get rid of this. So we need to BFS from root. Yeah. Okay, so we need to BFS from the root and from the last returned. what do we want to do here? Farthest return node will be, I suppose, just any node, right? So that will be root dot distance 1 is greater than end 1, greater than root dot distance 2. Distance 1 is bigger end 1, otherwise end 2. This is going to be a node, I guess. Okay. So now, this is disgusting, man. This is, ugh. We have 9 different queries, and there are 3 different cases. Yeah, so I think we just need to do this part now. We don't need to do, we need to do this too. But in order to do this part, we need to find the best other node. Okay, well, I guess BFS from the root and then BFS from farthest distance, and then dot distance 1 be equal to and dot dist. Do the same thing here, distance 2. Okay. So node best equals n well equals null, or node nn in nodes. Nn dot distance 1 equals the min. So min is like the answer from the root. So if this is true, then well, if this is not true, continue, because we're looking for the right answer. So if this is true, best equals null, or best dot distance 2 is greater than nn dot distance 2, then best equals nn, should be greater. What? Greater. Okay, thank you. So now this is the best node that we have. So in this case, this should be, well, n1 equals best dot index. Okay. So if max, or if min equals max, then in that case, farthest return node is going to be equal to nodes at node returned. So now we have the answer in this case. Otherwise, we move closer to the answer. We can't only hit this. Eventually we gotta hit one of these two. So here, if we take one step closer to the answer, then farthest return node can be equal to nodes at node returned. and that should be fine. Yeah, I think this might actually be okay. Let's try it. So we've got 1, 2, 3. So what do I answer for this problem? I say the closest node in the distance. So the closest node will be 1. The distance will be, maybe let's say the distance is 2. Let's say it's 2 and 3. Okay. So now they are asking about 2 and 3. Which one's closer? Maybe 3 is closer. So 3 is closer, the distance is 2. Okay. Now they're asking about 1 and 2. Which one is closer? Oh, they're asking about node 2. So node 2 is closer, and the distance is 2. The answer is 3 and 2. AC. Okay. I don't know what I think. I think I'm going to submit it. It'd be convenient if this were right.
Problem F2 got wrong answer test reason.
I see. I see. Okay. Why is that? So first, well, it would be really nice to know why this were wrong. First, I get the root. Let's first count how many queries I make. So this is 1. This should be 9 at most, if my math is right. And then this should be the 11th. So I should be at 11. Yeah, okay. So then okay, so this gets the root node, BFS from node 0. Okay, so these are my 2 endpoints of my diameter. Good. Now the root is the one that minimizes So this seems fine. So I get the root correctly. So now I get the distance from stuff to the root. My current best is the distance returned. Yeah, so if it's bigger than the current best, that means I've gone too far. Max equals mid minus 1. Yes, this is the max current distance. This might be quite big, actually. This isn't necessarily 9 queries. Yeah, this is fine. Never mind. This is the max distance, not the max yeah. So if min is not equal to 1, wait, min, yeah, the distance is the farther. So if min is not equal to 1, throw null. So the farthest return null, or farthest return node, is one of these two, I guess. But it has to be set. Yeah, it doesn't have to be set. When does it not have to be set? If it's 3, I think. This might not get set. If farthest return node equals null, then BFS from root and from farthest return node. Get the right one. I think that would be it. Do I even use this answer node anywhere? Yeah, I don't think so. Okay, so in this case, we want to this doesn't count as a query, right? Cool. We can ask at most 11. So 1, 3. Maybe we pick 1 and 2. The distance, or the closest one is 3, and the node is going to be 1. Uh, 1 is closer, the distance is still, oh, this isn't right. Okay. So the closer node, wait, the closest node is 3, and the distance is going to be 2 plus 1, so the distance is 3. Okay, 1, 5. The best node will be 1. The distance will be 1. 1, 3. Why 1, 3? Oh, okay, fine. So the best node is going to be 3. The distance will be 2. There's 3. Distance is 3. Yeah. 2, 1, or 3. better node is 1, distance is 1. 2, 1. Yeah, I guess that's right. Alright, I figure the bathroom, but I'll be right back. So still wrong, unfortunately, but on the bright side, we now know that it wasn't that we're asking too many queries, it's that we're getting the wrong answer, which is, I guess, better than the alternative, because asking too many queries is hard to fix. Getting the wrong answer is less hard to fix. I don't know that I have time to make a randomizer, because making trees is a little hard. Yeah. So I think it's just look through it, figure out why it's wrong. So could this be the issue? If the distance returned is too big, then the farthest node is this thing here. If the min is not equal to 1 through null. Okay, so this is always fine. We find a better min. This is not fine at all. This is an issue. Yeah, this is wrong. That's just not true. Yeah, that's the issue. So you could have like a really big tree. Like you could have some stuff over here. You could have some edge. could hit this other edge here. And then, I guess you pick this here, right? So now you set the max distance to 4, but the distance isn't really 4. Well, if we do this wrong, we're gonna just not be right, I think. This is just a wrong solution now. This will TLE, because it'll take too many queries.
Problem F2 got wrong answer test research.
Wait, wrong? Why wrong answer though? Let's try just doing this, just like modifying the old version. Oh, now we have to do this. Yeah. I suppose this is worth a shot. These are mostly Hail Marys at this point. This one should not be getting it wrong though, so that's an issue, I think. Farthest node is null. Or maybe it's asking too many queries, I guess. That's possible, but it's unlikely. So the farthest return node is this or this. Okay. So BFS from the farthest return node, BFS from the root. So if dist1 is not equal to min, continue. If best is null or best.dist2 is greater than this thing's dist2 is the distance from the farthest return node. Yeah, this should be right. We want to find the thing, the closest thing to the farthest guy. Yeah, this should be fine. So when can this be null? Well, let's do the Hail Mary submit then to see if we can figure out what it is. If it's greater than 11. Not true. Okay, inquiries equals 1. So I guess just submit this to try and get information. I don't know if we'll even get a verdict. But it seems like we're just wrong, which is very odd. Yeah. I don't know why this is wrong. All very odd. The best things index. Dist1 is the distance from the root. Dist2 is the distance from the farthest return node. That should be uniquely defined. Yeah, I don't know. Alright, well. How'd this look? Probably not great, right? So 24th place. Silenex beat me. Good job, Andy. Well done, sir. And UCF. I don't know. UCF did alright, I guess. For Div 2 round, not great, but okay. Alright, well, let's go over the problems. All but F2, I guess. So, here we go. So problem A was the easiest problem of the set, as usual. So you have to, what is it? Yeah, you have to find for all like pairs of numbers between 1 and n, the pair with the biggest GCD difference. So maybe like n is 13, and you want to find, like among all pairs, you want to find the pair with the biggest GCD, but those two numbers can't be the same. So since they can't be the same, the GCD can't be one of, or it can't be, yeah, it can't be the bigger of the two numbers. So like the biggest you can do for n equals 13 would be 6 and 12, because the GCD would be 6. So basically, when you take the GCD of two numbers that are different, you have to remove a factor from one of the numbers, because, yeah, like you can't have all of the factors of both of the numbers, because if you do, then the two numbers are the same. So you have to remove one factor from one of the numbers. And if you remove a factor of 2 from the bigger number, then you can always just take the smaller, like whatever that bigger number divided by 2 is. So if you have like 12, you can do 12 and 6. You can't do 13 in anything. Like the biggest, so this will always give you 6, I guess, and then you can't do better than that, because if it's odd, its biggest factor will be smaller than it over 2. So yeah, so that, I guess that's just solution. There you go. There's solution to A. Cool. All right, B, GCD compression. This used a very similar idea, just like it's GCD, but you only care about two things. So you're given some array of numbers. Maybe you're given like 1, 3, 2, 6, 5, 2. And you want to, what do you do? Oh yeah, okay, so you get to add two numbers together. You get to add pairs together. So maybe you add these pairs and these pairs. So now you get 4 and you get 8. And then you remove two numbers from it. So the pairs that you add together, if they have the same parity, then the sum of those two numbers will be even. So you can add together pairs of odd numbers, and you can add together pairs of even numbers. And then at the end, the GCD of all of those things will be 2 or more, because all of those things will be divisible by 2. And this is always possible because if you have an odd number and an even number, so if you have like a 5 and a 2, so you've got one extra unpaired odd and one extra unpaired even, then you can delete both of those. If you don't have one extra unpaired odd and one extra unpaired even, that means these last two numbers are either going to be two even numbers, in which case it's okay to delete both of them because now everything in this left side is all paired up. Or if it's not two even numbers, then it's going to be like two odd numbers, and then you can also delete both of them, and everything will still be paired up. Cool, so there is the solution to that problem. Let's look at problem C. Oh, did I get it wrong, or is it system testing? Yeah, it looks like it's just system testing in a weird way. Okay, so here's problem C, number game. Yeah, this was a really good problem, I thought. I really like this problem. So you have some number, and there are two things you can do. You can do like x minus minus, or you can like x divided by equal some odd factor. So if you do it like on paper, there are a couple things you'll see. You see 1 loses, obviously. You see 2 is a winning state, because anything that can reach 1 will be a winning state. So 2 wins. And any like odd number, you can just divide out the entire odd number and win right away. So any odd number will win. If you have 2 times an odd number, then, well, okay, if you have 2 times an odd prime, then your only choice is to divide out this odd prime here. And when you divide out the odd prime, then you'll get the number 2. I say it's your only choice. It isn't actually your only choice. So you can divide out the odd prime. If you divide out the odd prime, you get to the number 2. Your other choice is to subtract 1, but when you subtract 1 from an even number, you get an odd number. So either way, if it's 2 times an odd prime and it's your turn, then you're going to leave your opponent in a winning state. So your opponent's going to win, which means you lose. Okay, cool. So that's a bunch of cases. What other cases are left? Well, it can be like 2 to some power. And if it's 2 to some power, then your only choice is to subtract 1. And if you subtract 1, then you lose. Assuming it's not 2 to the power of 1. So if it's 2 to some power, you lose. What if it's like 2 to some power x times like some odd number? Not necessarily prime. Well, if this is the case, then you can make your opponent lose by taking out this odd number, and now your opponent will be in this state here, and your opponent's going to lose. So this you can always win by. And that leaves one more case left. The only thing left is if you have 2 times like some odd prime times some other odd number. So one example would be 30. 30 is equal to 2 times 5 times 3. So if you have this, you can get rid of this odd number, and when you do that, then you put your opponent in that losing state, and that's like similar to doing that. So those are all the possible cases, and you can just iterate through them manually and see which ones you'll win for, which ones you lose for. All right, so cool. Let's look at a slightly harder problem, problem D. So yeah, problem D was, I guess, interesting, I guess. So you have a series of numbers, So let's look at like 1, 4, 3, 7, 2, 4. And what you have to do is you have to like choose k of them and keep them in the same order. And then you want it so that you're going to look at all of the even numbers. You're going to take the max of all of those. Then you're going to look at all of the odd numbers, take the max of all of those. And then whichever of those maxes is smaller, that's what your final answer is. So I guess let me just check something really quick. All right. So yeah, so you're gonna take the even occurrences of the things you pick, and then the odd occurrences of the odd occurrences of the things that you pick. So maybe you pick 4, 3, 7, 4. Then you have 4, 3, 7, 4, and you're gonna take the bigger. Wait, what do you take? The smaller of the two maximums, and you want to minimize that. So basically what that means is you can either ignore all of the even indices that you choose, or if you don't ignore all of the even indices, you can ignore all of the odd indices. And now you're left with some group of the numbers that you've chosen, and you want the biggest number in this group to be as small as possible. So in this case, if you ignore the 3 and the 4, so that would be, I guess, the even indices if you do one based, then you're left with the 4 and the 7, and you want the biggest number to be as small as possible. So in this case, this would be a pretty bad way of choosing numbers because we skipped the 1 and we skipped the 2. But basically what you can notice is that what we've kind of done here is if we like decide whether we're going to skip the even numbers or the odd numbers, then half of the numbers in our array we can use for either position, or half of the numbers, some of the numbers in the array you can choose to use for either position. The rest of the numbers you can only use for the position that you're deciding to ignore. So let's say if you know your cutoff is going to be 3, you know your answer is going to be 3, then it's okay to have this in either position. You can have this in either position, you can have this in either position. But these numbers here, since they're bigger than 3, they can only be in either the even positions, in which case you keep them, or they can be in the odd positions, in which case they're in the max that you're going to consider is the higher max, so you skip all of those numbers entirely. So so basically what you can do is you can binary search what this answer is going to be. And as you binary search the answer gets bigger, there become more numbers that you're allowed to keep. And as the answer gets smaller, there are fewer numbers that you're allowed to keep in whichever of the constrained indices you're going to use. So I guess that's kind of the solution idea. So you binary search this. And after you binary search this, you just need to see, okay, can we keep k items total? And you can do that pretty easily. So it's, I guess you can just use a greedy. So you know if, like, let's say this is going to be our first index and we're skipping the odd indices. So we're skipping, I guess, yeah. So we can say we're skipping the odd indices. In this case, you'd want to skip the even indices. But so we can keep this because it's circled. And, well, we can keep it because we're skipping the odd indices. So we're at index 1. We can put whatever we want here. It doesn't matter. So we'll keep this. Now we're at the 4. So this is an even indices, so this even index, so this matters. So we can't keep the 4 because the 4 is bigger than this 3 value that we're binary searching. So we don't put it here. And I guess we just move on because we can't use the 4. So the next thing we might be able to use is this 3. And the 3 is smaller than or equal to 3, so we can keep it. And now we have this thing, which we're going to ignore anyway, so we put the 7 here. And now we have this next index, and this index is important. So instead of like skipping the 2 or waiting for the 2 to be put down somewhere later, we can put the 2 down here because it's like circled, it's under our binary search value. And then we're going to see, all right, what's the next thing we can put down? Well, we can put down the 4 because this is some index that we don't care about. because we're going to delete it anyway. So here we can pick 5 numbers if this 3 value that we're binary searching is small enough. And if 5 is bigger than k, then 5 is bigger than or equal to k, then 3 would be a valid answer. Otherwise, 3 wouldn't be a valid answer. And you can binary search from there. All right, that was very long and kind of an unnecessary explanation, I think. E was pretty easy, I felt. Let's talk about that. So in problem E, you're given 2 different strings. So the first string is, well, they're both binary strings. And maybe you want to make this string. So you want to turn this into this string, and in a given operation, what you can do is you can select some elements. Maybe you pick these elements, and you take this substring and you rotate it by 1. So this 1 would go here, so now you'd have a 1. The 0 would go here, so now this would be 0. This would go here, you get a 1, and this would go to this spot here, so this would be 0. So you can replace all of these indices, and then after you do that, you have some new string, and you want to convert it into this string here with the fewest number of steps possible. Okay, so how do you do that? Well, the first thing you can notice is since we're picking subsequences instead of substrings, we can just skip like this pair, and this pair, and this pair. We can imagine deleting them from the array entirely because they're both zeros, so there's not really any reason to swap these. And similarly, these 2 are both 1s, so we can skip these as well. And now what we're left with is we're left with just a string that looks like this. Oops, sorry, you can also skip this first one because they're both 1s. So now we're left with just this string, and this string is pretty simple. Like, it's pretty obvious that you only have one move you can do. You can select both of these, and then you can rotate them, and that'll swap them. So basically, we've simplified this problem down to something where we just have 0s and 1s, where we have like mismatched pairs. And since we've deleted everything that matches, we don't really care about the instances on the bottom. All we care about is what's on the top. And we want to move each 0 to a 1's position, and then move each 1 to a 0 position. The other thing to notice is it isn't helpful. Like, we're going to pick some sequence of numbers. Let's make this a little bit more complicated so it's easier to explain. We're going to pick some sequence of numbers, and it's never helpful to pick 2 zeros in a row. Because if we pick 2 zeros in a row, this 0 would move to this 0's position. And then if we pick 2 1s in a row, this first 1 moves to the second 1's position. So basically what we want to do is we want to pick one of these 0s, one of these 1s, one of these 0s, and one of these 1s. And if we move all of these over, then we can get rid of all of these effectively, because each one moves to the next one's position. If we have something that looks like this, we aren't allowed to pick a 0 at the beginning and also at the end. Like, that isn't helpful, because now we've picked more 0s than 1s. So like this 0 that we pick at the end would move to another position, but that other position would be a 0. So you have to pick like the first 0 and the first 1, and then you keep doing that in a row. So now you want to go through the array as few times as possible, where each turn you can pick any number of 0s and 1s, as long as they're ordered 0, 1, 0, 1, 0, 1. And also, well, I guess that's kind of the only constraint. Oh yeah, also, like, the first number you pick is different from the last number you pick. And that's just the number of moves that you can do. So you can do this with a tree set pretty easily. You want to pick the first 0, and then you want to pick the first 1. And then after that, you want to pick the first 0 again, and then you want to pick the first 1. And I guess the reason that works is if you imagine compressing these ranges into just, you have a bunch of 0s here, then you have a bunch of 1s, then you have a bunch of 0s, then you have a bunch of 1s, then maybe you have a bunch of 0s again. Well, this means you can have, you can pick 5 numbers total, or you can pick, there are 5 ranges, so you can only pick once from each range. But really, you can only pick 4 ranges total, because you can pick 1 here, 1 here, 1 here, and 1 here. And if you try and pick this one, then you'll start and end with the same number, so it won't be valid. So you can just do this naively with the tree set, and that will get you the answer. All right, let's talk about F1. So F1 was, I think it was an interesting problem. I don't know how to extrapolate it to F2, but I can talk about how to do it for F1. And then I get really, really close. So mine does it in, I think, 12 queries. Maybe the right way is just completely different, but I'm not sure. So you have some tree. And I think maybe this is a good tree. So you have some tree, and they have picked 2 nodes on the tree already. So maybe they picked this node, and maybe they picked this node. And we're going to draw this path in between these 2 nodes, because that path is interesting. And now what you get to do is you get to pick some other node, or you get to pick some subset of nodes. So maybe you pick like this node, and this node. And they will pick some node. So what they're going to do is they're going to return the length of this path plus 2 times the distance from the node you pick to some node on the path, to the closest node of the path. That's the value that they return. That's equal to the distance to the first node plus the distance to the second node. So what you can do is, first, if you have some, let's say we were able to get some node on the path, and we can do this pretty easily. So all we need to do this is just like pick every single node, and one of the nodes they return will be the node on the path. Those are the only nodes with the minimum sum of distances. Okay, so now we have some node on the path. Let's say we have this one, because it's kind of in the center of the tree. So now what we can do, so that's one query, and now we can spend log n queries to find this farthest node here. So in order to do that, what we can do is we can binary search how far we need to go. And like we can binary search, let's say we're going to check distance 2. So we're going to pick all nodes that are distance 2 from this node. So that'll be this node here, this node here, this node here, and this node here, and also this node here. And what we can see is that it will return this node here, and it also return the distance 1, 2, 3, 4, yeah, it'll return the distance 4. And since that distance is equal to the length of the path, we know that this node is on the path. And we can keep expanding our circle of nodes that we choose until we find a node that isn't on the path. So like as we expand our circle, we'll have nodes on the path continually, and then eventually we'll have nodes that aren't on the path. And we can binary search that value, and we can do that in log time. So that takes log n queries. And then finally, after we do that, we'll be able to find this farthest node. This will be the node that gets returned, the farthest node from our start. So we'll have this node here. And we also know the length of the path. So we can find, or we can query all nodes that are the correct length, and then that will return the other node that they're thinking of. So that's one more query here. So this takes 12 queries for me. This is 10. So it's 1 plus 10 plus 1. And you might be able to do better somehow if you are more careful. Maybe if you start at the centroid, you can make the log, instead of making it 10, you can make it 9. But then the issue with doing that is that you don't know the length of the path, but as you look for stuff, you can get a better bound and length of the path. It also seems like centroid decomp might be very helpful, because it seems like you learn both which centroid to go to next, and also whether that centroid is better. So it feels like if you're familiar with that technique, that would be a good way to go. That's just my idea. So anyway, I hope you enjoyed the set. Hope your rating went up if this was rated for you, or otherwise I hope you enjoyed the problems as much as I did. See you later.